Hello everyone, in this video I'm going to go over the Chem 118C workshop 14 for ATC. So this worksheet is going to go over the dicarbonyl compounds, and for these reactions we are going to do Claisen condensation, mixed Claisen condensation, intramolecular Claisen condensation, benzoquinone synthesis and reactions, beta-carbonyl ester synthesis and reactions. So for Claisen condensation reactions, they require at least 2 alpha hydrogens, where the first alpha hydrogen is used to form the enolate ion, our nucleophilic enolate ion, and our second alpha hydrogen is to quench the bad leaving group that is the alkoxide in the mechanism. So let's do the first example, which is to predict the major product for the following. We see here we have a carbonyl and 1 alpha hydrogen here. So since we do not have 2 alpha hydrogens, this will give us no reaction. So the first alpha hydrogen will be used to form our enolate ion, our nucleophilic enolate ion. So after we form the nucleophilic enolate ion, we are going to look for an electrophile to attack, which we could use another version of the carbonyl itself. So this nucleophilic enolate ion will attack the electrophilic carbonyl, open the carbonyl onto the oxygen right there. And what I did here was I starred the attacking carbon, dotted the carbon being attacked, to keep track of what groups are attached to which groups. So after that step, I combine the groups. I see that this starred carbon here has 2 methyl groups and this ester group over here. And this dotted carbon used to have a carbonyl, but since we kicked up the double bond onto the oxygen, this oxygen will have a negative charge now. And now this oxygen is going to reform the carbonyl, kick out the bad leaving group. And now since this is the bad leaving group, we do not have a second alpha hydrogen to quench that bad leaving group, so it will go back and react with the carbonyl and reverse back to the original compound. So that's why this will give us no reaction. Now let's go over part B. Now we see we have 2 carbonyls. This compound here has no alpha hydrogens because this carbon here already has 4 bonds, 1, 2, 3, 4. This is not an alpha hydrogen because that's an oxygen right there. So we see in the other compound, we have 3 alpha hydrogens, which accounts for the at least 2 alpha hydrogens to proceed with the Claisen condensation reaction. So the first step here is to use the strong base to deprotonate the alpha hydrogen, make that as enolate ion, and then we do the resonance here. We see that the carbon is less stable, holding the negative charge than the oxygen is, which is why this carbon here is the attacker instead of this negatively charged oxygen over here. So this nucleophilic oxygen carbon over here will attack the electrophile, kick up the carbonyl bond up there. I start my attacking carbon, dot my carbon being attacked. I connect those 2 carbons together, making the new bond. And then I keep track of what groups are attached to which. I see that this dark carbon is attached to this ester group, this dotted carbon is attached to this benzene ring, and this alkoxy group with this O- group now. Now when we reform the carbonyl, we kick out the good leaving group. Now this good leaving group has a alpha hydrogen between these 2 carbonyls to deprotonate and quench the bad leaving group. And then now we have an irreversible step here, which is our rate determining step, whereas the previous steps were reversible, because right after we quench the bad leaving group, this reaction will proceed forward and just protonate the negatively charged carbon if we have an acid workup second step over here. So in the third example, we have 2 compounds that has alpha hydrogens, but we're going to deprotonate the alpha hydrogen that is the most acidic. So we see here the ketone alpha hydrogen is more acidic than the ester alpha hydrogen because when we look at the conjugate base of the ketone acid, we see that this carb anion here is able to do resonance with the carbonyl group, whereas the ester conjugate base can also do the resonance with the carbonyl group, but it has competition with the alkoxy group over here. Since this lone oxygen here has 2 lone pairs of electrons, those 2 lone pairs of electrons can do resonance and compete with the resonance of the carb anion here, decreasing the acidity of this compound. So that's why we are going to deprotonate the alpha hydrogen of the ketone, form our enolate ion here, and then we're going to attack the more electrophilic carbon. So we have two electrophiles here. We have this carbon double bond into the oxygen and in the ketone. We also have the carbon double bond into oxygen and the ester, but the carbonyl carbon of the ester is more electrophilic because we have two oxygens bonded to that carbon, pulling or withdrawing more electrons, making this carbon more electrophilic than this carbonyl carbon of the ketone. So we're going to attack the more electrophilic ester with the nucleophilic enolate ion. I start the attacking carbon, I dot the carbon being attacked, and then I attack that electrophile, make the new bond between the starred and dotted carbon. I see that the dotted carbon is attached to a methyl group, an O- group, and an alkoxy group now. Now we reform our carbonyl bond, kick out the bad leaving group, and then this bad leaving group is able to get quenched by the second alpha hydrogen here. And then since we don't have a second acid workup step, we have this product here that is able to do resonance with these two carbonyls, giving us three resonance structures here. Now let's move on to the next part. Now we see we have a strong base, a multi-step predicted product over here. In the first step, we have an alkoxide ion, OCH2CH3, which is our strong base. We're going to look for our most acidic hydrogen, which is the hydrogen, alpha hydrogen between the two carbonyls. This alkoxide ion is going to deprotonate that alpha hydrogen, form our enolate ion. And this enolate ion can not only do Claisen condensation, but it can also do SN2 back from the beginning of organic chemistry reactions. This could serve as a nucleophile. If we introduce an electrophile like in our second step, CH3Br, we could use that nucleophile to attack and do SN2, kick out the good leaving group bromine there. And then the third step introduces another strong base, CH3CH2O-, which will deprotonate the alpha hydrogen since we have one more alpha hydrogen, form our nucleophilic carb anion there, do another SN2 reaction with the fourth step here. And then after that, we are going to protonate the ester and hydrolyze that all the way down to the carboxylic acid. And once we hydrolyze this all the way down to the carboxylic acid, we introduce heat to do the decarboxylation reaction and get rid of the carboxylic acid and emit that as CO2. And this is the tautomerization step where we convert the enol into the carbonyl here. So a tip to keep track of what groups are attached to which when you do the attack is to start the attacking carbon and dot the carbon being attacked. And after that, when you do the reaction, you make a new bond between those two carbons, the starred carbon and the dotted carbon. Now let's move on to the next problem here. We see that we have benzoquinone with acid HCl. So since we have acid, we're going to look for our most basic atom, which is oxygen in this case. It could be either one, since this is a symmetrical molecule. This oxygen here is going to get protonated, kick out the Cl- right there. And then this Cl- will attack the carbon of the ring, kick up the double bond over there, and neutralize this OH-. And then this structure here will equilibrate into the more stable benzene ring over here. And so let's do the synthesis problem of this over here. We see that we formed another ring with a cyclohexene. So whenever you say cyclohexene, that is an indicator of a Diels-Alder reaction. So we need a diene and a dienophile for Diels-Alder. So what we could do to convert this reactant into the diene is to use Jones, an oxidizing agent, to convert this hydroquinone into the benzoquinone. This will serve as our dienophile. And then our second step here will be our diene. So I'm going to redraw this dienophile in a straight orientation. And I'm going to draw this diene here. And these are the arrows of the Diels-Alder mechanism. This double bond is going to make a new bond between these two carbons. This double bond here is going to make a bond between these two carbons. And this double bond is going to make a double bond between those two carbons, forming our cyclohexene. And then this right here will automatically equilibrate into the back into the benzoquinone, since it is a more stable structure. So this is a two-step synthesis over here. Now let's go over the mechanism of this multi-step reaction. We see that we have a strong base, which is this alkoxide ion CH3CH2O-, that will deprotonate the alpha hydrogen here. And we could have either deprotonated any of these alpha hydrogens, since we have multiple sites. But in this case, since this is a symmetrical molecule, we're going to deprotonate this alpha hydrogen. It wouldn't matter. You could have also done this way. You would get the same answer as well. So once we deprotonate that alpha hydrogen from the enolate here, we do the resonance to show that this carbon with the negative charge is the nucleophile, not this oxygen with the negative charge, because this carbon here with the negative charge is less stable, making it more reactive. we see here that we could do a intramolecular reaction where this enolate ion can attack an electrophile on the same molecule, which we are going to form a 1, 2, 3, 4, 5-membered ring. Take that up there. When I would do this, I would store this attacking carbon, I dot that carbon being attacked, or I would have numbered this 1, 2, 3, 4, 5 and form the 5-membered ring here. Keep track of what groups are attached to which carbons. Since I labeled this 1, I know that this ester here is attached to carbon 1. Carbon 5 here has the O- group and this alkoxide ion there. And then we reform the carbonyl, kick out the bad leaving group. This bad leaving group will have to be quenched by cyclic alpha hydrogen, which we do have here. And once we quench that bad leaving group, we form this carb anion, which will get protonated and give us our Claisen condensation product over here. And then our third step, butoxide, is another strong base, which will deprotonate our most acidic hydrogen. And that most acidic hydrogen is going to be the alpha hydrogen between these two carbonyl compounds. Since the conjugate base of this acid will be able to resonate between these two dicarbonyls over here. And then this nucleophilic carb anion here can serve as an SN2 nucleophile if we introduce an electrophile like phenol CH2Br, which will attack that electrophile, kick out the good leaving group, and then we have this SN2 product over here. And then we introduced acid and heat, which will hydrolyze this ester, and the heat will do the decarboxylation reaction, which gets rid of that carboxylic acid after we hydrolyze it, and form the enol, and then we tautomerize that enol back into the carbonyl. So the first step here is to protonate the ester alcohol, use the water to attack that carbonyl carbon, kick that up there. This is the proton transfer step. I'm going to protonate the group that I want to leave, which is this alkoxide group, deprotonate the group I want to stay, which is this water group. So after this proton transfer step, we reform the carbonyl, kick out the good leaving group here. And then once we do that, we're going to have this carboxylic acid like group here, which this positively charged oxygen gets deprotonated by the water. And then after that, we do the decarboxylation step with the heat, where this oxygen here is attracted to that hydrogen, positively charged hydrogen. This bond between oxygen and hydrogen will make a double bond between this oxygen and carbon, forming our CO2 molecule here, where it breaks off and forms the double bond right there, giving us our enol, which is an alkene right next to an alcohol. And then this is the tautomerization step here, where we go reform the carbonyl and then protonate the carbon of this alkene over here. And then we deprotonate this carbonyl oxygen to get us our final products here. And now this is the last problem of this worksheet, which is the acid base or pKa ranking acidity problem. We see here that this is our most acidic compound, which has the lowest pKa, because if we look at the conjugate base of this conjugate base negative charge is super stabilized by these two dicarbonyls nearby. There's no R groups or electron donating groups competing with this resonance. So this is the most stable here. And to determine which compounds are more acidic, you look at the conjugate base of it and see the stability. If the conjugate base is more stable, then that means that it came from a more acidic acid. Whereas if we look at this case over here, this is less acidic than this because we do have the same resonance over here, but we have two R groups this time, which donates electrons to the resonance, decreasing the stability of the negative charge here, since negative charges repel each other. Now let's look at the next one, which we see here. This is even less acidic because this alkoxide ion has lone pairs of electrons itself, which is able to do resonance and compete with the resonance with this carb anion over here. Even more so on this compound, since we have two alkoxide groups here, which is going to compete with the resonance of this carb anion over here. And then we see here, this is even more basic or less acidic because this oxygen conjugate base with the negative charge is not able to do resonance. We see here, this is a range, and it also depends on like the professor or like the researcher. We see this conjugate base with the negative charge is able to do resonance, which is more acidic than this ketone over here, because this ketone has the R group, which inductively donates electrons, destabilizing this resonance with the negative charges because negative charges repel each other. And then the most basic one would be there's only one carbonyl with the ester that has a lone pair of electron in the alkoxide oxygen, competing with the resonance of the carbanion resonance structure over here. So these ones have two dicarbonyls stabilizing the conjugate base more so than these compounds with only one carbonyl structure. So yeah, please subscribe, like, and share this video, and hope that helps.